Okay, we're ready to get started. So as you know, today is going to be our last lecture covering material for midterm 2. Your midterm 2 is not cumulative. It only goes from your end of midterm 1 all the way until today. I'll post more detailed information in a Green Learn announcement later today after we finish this lecture. And the other question is, are there going to be people who want me to hold like extra office hour tomorrow? Because yesterday my office hour only have 3 people coming by. So let's raise your hand if you want me to host extra office hour tomorrow. I don't know what time it is, but like raise your hand if you want me to hold an extra office hour tomorrow. Sorry. So I guess no. Okay. If you still want to set up an appointment with me, send me an email, and we can discuss anything tomorrow. Nevertheless, since I don't have a big population want me to hold extra office hour tomorrow, I guess I will not do that. But if you need me, send me an email or get an appointment. All right, with that in hand, let's get started to finish up lecture 14. I call it lecture 14. We're almost at the end of the quarter now. Okay, so this one is lecture 14. So at the end of lecture 14, so remember when we were talking about chapter 5, right? What we're doing is get an idea about how to use the tabulated data to solve for state functions like Gibbs free energy, entropy, or enthalpy for chemical reactions. We also carefully went over how those tabulated data are being generated, like how they're being calculated or measured, right? So remember that long 9-step derivative for the standard conventional molar entropy of SO2. That's one of the example we did together. It's long, it's a little bit tedious, but it shouldn't be any hard or surprising to you. All right, and at the end of chapter 5, we have 2 more things to cover. The first one is the standard entropy of reaction. So again, for a general reaction, so on the left-hand side, you have 0 that goes to the stoichiometric coefficient of different substrate, reactant or product, right? So the stoichiometric coefficients are negative for reactant, positive for product. So that's a general reaction we went over several times now. And when we're calculating the standard entropy change of the reaction, effectively what we're doing is you're talking about the delta S at the standard condition, which means if it is a gas, it's an ideal gas. And we're talking about pressure at 1 bar and at certain temperature. And you can calculate the delta S of the reaction using our tabulated conventional entropy data. So there is one example question here. Just use the appendix data to find out the entropy of this reaction, which is ammonia reacting with oxygen to form nitrogen and water. So basically, you just go to the table and find out these species in the table and set up your calculation using the stoichiometric coefficient. So some of the things you can get by just looking at our calculated data. Right, so first of all, for example, in this case, we're talking about a reaction with a very negative entropy. So what that means? We're talking about the entropy of this reaction decrease comparing from reactant to product. And it sort of makes sense. If you look at the reaction, we start from like 7 molecules of gas molecule, and we end up with only 2 molecules of gas. So it sort of correlates with the number of more of gas that's decreasing in the reaction. We'll go over that in the more detail when we talk about actual equilibriums. All right. And the last topic is the standard Gibbs free energy of reaction. So we went over calculation of the standard enthalpy of the reaction or heat of the reaction. We carefully went over the calculation for the standard entropy change of the reaction. So then the Gibbs free energy just becomes very obvious because we know G equals to H minus Ts. That's by definition. Right, so there are several ways you can do it. Like what we did, first of all, you can calculate the standard Gibbs free energy change from the tabulated data. So the delta G for a reaction, you have the coefficient times the standard and standard molar Gibbs free energy of that specific chemical in the tabulated data. You can calculate it that way. Or if in your data or in the question it is not given the standard Gibbs free energy or standard Gibbs free energy of formation, you can calculate that Gibbs energy of formation coming from the standard enthalpy of formation and standard entropy of formation. So like these are just connected. So basically what we're using is the equation G equals to H minus TS, and then these relations here. So one of the example question is, for example, in this problem, it's asking you to calculate, it asks you to only use the delta H and also the S naught value to calculate delta G formation for magnesium oxide and compare your result with the tabulated data. So in that case, you shouldn't be using this column here. You shouldn't just go into that table and get me that number. It doesn't matter how you get that number. What it matters is how you set up the calculation. So in this case, the way we set up the calculation is we know the heat of formation. So delta HF is known. So this part is known. We need to find out the delta F, or heat of formation, or entropy of formation for magnesium oxide. And the way you do that is you set up a formation reaction from its elemental component. So in this case, you have magnesium reacting with 1/2 oxygen to form your magnesium oxide, right? So that's your formation reaction. You can calculate the entropy change of this formation reaction to get your entropy of formation of magnesium oxide, all right? And basically you go to the table and find out those conventional entropy of different chemicals and using the stoichiometric coefficient together to solve for the entropy of formation for magnesium oxide. And taking together, you then have your delta S formation, and you can use your G equals to H minus TS to solve for your final result. So one thing I want to make sure I highlighted is the unit in the table for your conventional entropy is in joule per mole per Kelvin. And your unit in your enthalpy and Gibbs free energy is in kilojoule. So keep in mind there's a unit difference when you're reading the table, and make sure you take consideration of that kilojoule to joule differences when you set up your calculation. It's one of those easy points you could miss and lose like 3 points unnecessarily. All right, and taking together, you can set up the calculation and get your standard free energy of formation for magnesium oxide, and that number is what you see in the table. And again, in thermodynamics, you have different ways to solve for the same result, and it's always a nice sanity check to make sure you have it correct. Okay, so that's the end of chapter 5. This chapter should be a pretty straightforward chapter. It's using the tabulated data to solve for your, well, free energy, enthalpy, or entropy, and know how those tabulated data comes from. Do we have any questions before I move on? Yes?
So how would you solve delta G if temperature wasn't constant? Or like, will that not come out?
No, that wouldn't come out in this class at least, because if the temperature is not constant, then it becomes way more complicated. Yeah. And also keep in mind your enthalpy might also depend on temperature, right? So that means your overall process will become very complicated. Okay. All right, let's move on to our lecture 15. This tells you like how ambitious I am in preparing my lecture notes. But nevertheless, in lecture 15, we have 3 topics here. So we're moving from a generalized reaction and standard condition, and we're trying to go a little bit deeper into the concept of chemical equilibrium. So I hope now it feels more like a chemistry class for you. So in this chapter, we will talk about ideal gases. That's our simplest model we can imagine of. So I'll start by ideal gases, and some of the rules we derived in this chapter will also be applicable for other systems. But let's just get started for ideal gases. Well, first go over a quick introduction to ideal gas mixture. So instead of having any reactions taking place, before we jump into reactions, we're just talking about what makes a mixture of ideal gases, and how do we understand the chemical potential in ideal gas mixture. And then using the ideal gas reaction equilibrium, we will link the concept of equilibrium constant with chemical potential. So both of the terms we've seen before. So now it's one of those situations we're actually linking them in a specific chemical reaction and see how these two terms apply to each other. And at the end, we will talk about temperature dependence of equilibrium constant. We'll see how far we go. Okay, let's get started. So 6.1. So in this case, we're talking about chemical potentials in an ideal gas mixture. Or what exactly we want to do is, again, chemical potential is something we really are interested in. That's one of the inherent properties, or one of the intensive properties of a specific chemical species. Now what we want to do is link that chemical potential to something that you can experimentally measure. So we know we have a way to solve for to measure for the chemical potentials. So in this case, before we get started, let's do a quick derivation and see what exactly is that chemical potential. So this will serve a little bit like a review. We went over chemical potential in lecture 12 or 11. I don't remember the lecture note, but we went over the chemical potential before. So chemical potential mu, this one is an intensive property. So when we say it is an intensive property, what we're saying is the chemical potential of a system is independent to the size of your system. It's a little bit like temperature. So remember the analog we made? So when you have temperature, right? So the heat always go from higher temperature to lower temperature, or the equilibrium always go from the higher chemical potential to the lower chemical potential. So like temperature, your chemical potential is an intensive property. So that means it is independent from any of the extensive properties, like number of mole or volume. Or, in general, we can write our chemical potential, mu, as a function of pressure and temperature. So both of them are intensive properties. And again, the reason it's independent from N and V is that these are extensive properties. And if we think about the definition of chemical potential, so we have mu I is defined to be the partial derivative of G over number of mole, the change of number of mole of that species Ni, with other terms kept constant. So if you think about this definition, when we're talking about the chemical potential of a pure substance, that means we're going to have one substance. It's not changing phases, just one substance in one phase. Then what we have is this mu I just equals to your G over N. That becomes the molar Gibbs free energy. So the chemical potential of a pure substance just equals to your molar Gibbs free energy, or Gm. And for any Gibbs free energy, we have our Gibbs relations. So G equals to negative SdT plus VdP. All right, so we're using lots of the things we derived before. So here's where we make a link to all of them. So taking that together, what do we have? So we have the du equals to derivative of the molar Gibbs free energy. That equals to the molar entropy dt plus the molar volume dp. So that's what the chemical potential of a pure substance is. I will come back and revisit it. Now, typically, when we're considering the ideal gas process, let's just simplify our life a little bit by assuming it is an isothermal process. We can later on and see if we can drop this limitation. But right now, let's just assume we're talking about an isothermal process. So dt equals to 0. And we have the derivative of your chemical potential that's equals to Vm dP. And remember, we're talking about ideal gases. So some of the things you know, so Vm equals to volume divided by number of mole. And for ideal gases, you have PV equals to nRT. So that's nRT divided by nP. So these cancel out. We have an expression of your chemical potential in pressure and also the change of pressure. So RT over P dP. Well, so obviously, if we do the integral on both ends, we get the change of your chemical potential in its final state versus original state. So taking derivative on both ends, we have our chemical potential at constant T, but some final pressure PF minus the chemical potential at constant T and some initial pressure P initial, and that equals to the integral on the right-hand side, which is RT over P dP. Now R and T are constant, so we can take it out. We get RT ln P final over P initial for ideal gases only. All right. And now if we're looking at that standard pressure scenario, we can add that superscription, that little nod there means it's like standard condition. It's ideal, it's at 1 bar. So T 1 bar equals to your, sorry, what I want to say is here, the difference here, the mu of T, some pressure, minus that standard chemical potential. The difference becomes RT ln some pressure over that standard pressure P naught. All right. And what exactly does it mean? So we can get some like quick take-home message by just looking at this relationship here. So on this plot, on the y-axis, that's what we have on the left, right? So that's the difference between your chemical potential of that ideal gas, of that pure ideal gas at some pressure, minus the standard chemical potential at 1 bar. So that's on the y-axis. On the x-axis, that's the P over P naught. So this one is like a logarithm function. So if we look at several of the points here, for example, if we pick a random point here, so we have the pressure is smaller than your standard pressure. So your chemical potential is a negative number, or your mu is smaller than your mu standard. And you can predict how the equilibrium is going to shift by just looking at how your pressure is different here. And likewise, if we're talking about a pressure that's higher, so when your pressure is larger than your standard pressure, you have mu larger than mu naught. And in addition, well, we are considering like extreme situation, when you have like pressure approaches 0. So your volume is approaching infinity and your mu is approaching negative infinity. So your chemical potential is like decreased with the temperature approaching, with the pressure approaching 0. So that's basically the first thing we did is we, again, redefine the chemical potential for ideal gases before we move on to talk about ideal gases mixtures. Right? So right now we have a way to calculate your chemical potential for ideal gases. Next step, we're ready to talk about the ideal gases mixture. So the first step is we define what chemical potential of ideal gases are. And then we start to talk about chemical potential in ideal gas mixtures. So before we do that, let's do a quick, more accurate definition of what exactly is an ideal gas mixture. So a few things need to hold true for ideal gas mixture. The first thing is, well, again, PV equals nRT. So N here, that's the total number of moles of your all species of gas. And your total number of mole of gases equals to the sum of each of the gas species. And then the setup becomes a little bit weird, if you may. So the way we think about it is, now imagine you have two chambers that are separated by a thermally conducting rigid membrane. And this membrane is only permeable to a certain gas species. Now we call it I. It can be any gas species we're interested in. The way we create that ideal gas mixture is, on the top, you have some kind of ideal gas, and on the bottom, you have that pure ideal gas I. Then by manipulating the pressure on both ends of your membrane, you can force that I to go in or out through that membrane. So for an ideal gas mixture, we say that at equilibrium, the partial pressure of the specific species I must satisfy Pi equals to its mole fraction I times P. All right, so that's a more accurate definition for an ideal gas mixture. It's at equilibrium, the partial pressure of that specific gas species, I, must satisfy the mole fraction of that species times the total pressure of your system. And whenever you see something like this one, like a star, it tells you that it's a thermodynamic property of a pure substance. It's not a mixture, it's just pure substance. So with that in hand, then we're ready to use whatever we just defined, the chemical potential of that pure species, and see how it performs when we're talking about a mixture. So in this case, when we look at the chemical potential of that specific gas I in a mixture, right? So now we're looking at a mixture with lots of different components, gas 1, 2, and 3, and etc. Now we're just looking at one of those components. So in this case, your chemical potential will have, of that specific species I, will have this relationship. Now this one is telling you the chemical potential of that specific species I is dependent on temperature, pressure, and mole fraction. And we build the link that for ideal gas mixture, the partial pressure is by definition your mole fraction times the total pressure. So that means if we're looking at the chemical potential of a pure substance I, its chemical potential is only dependent on temperature and its partial pressure. All right, with me so far? Okay, and again, in here, we have the partial pressure equals to the mole fraction times the total pressure. Or taking that together, we have the fundamental thermodynamic equation for an ideal gas mixture. So this one is pretty much similar to what you've seen before, but instead of just pressure, because we only have one species at the formula before, now we have now we're talking about a mixture. We're looking at that specific component I in an ideal gas mixture. So the chemical potential of that specific component I in the ideal gas mixture, so that's our mu I, using that same relations, you have mu I equals to that standard chemical potential of your species I at certain temperature, plus RT ln partial pressure of your chemical species I over the standard pressure P naught. Okay, so what are these terms? So this one is, again, this is what we discussed before for a specific pure substance. So in this case, the chemical potential of this pure substance I equals to the molar Gibbs free energy of that specific substance I. Okay, and then in here, this one is your partial pressure. And let's do an example together and see how it links to something we care about. Now, for example, this is example 6.1. So ask you to use this relationship, which we just shown before, to calculate the delta G for a process when the pressure of 3 mole of a pure ideal gas is isothermally decreased from 2 bar to 1 bar at 400 Kelvin. So in this case, we're looking at a pure ideal gas. So whenever we have that pure species, your chemical potential equals to the molar Gibbs free energy for a pure substance. All right, so what it asks for is the delta G is equal to mu final minus mu initial. And we have a way to calculate your mu final and your mu initial. So that gives RT P final over P naught minus RT P initial over P naught. Or we can further simplify it to RT P final over P initial. And you can plug in the numbers and translate that molar Gibbs free energy into your Gibbs free energy. So delta G equals to N times delta GM.
Where did the LN go?
Oh, yes, very true. Yeah, and if you see a typo in my lecture notes, just do send me an email and tell me like you find the typo. I'll go back and change it. Like this is one of the good example of that. All right, and by doing this calculation, we can get a very negative number. And you can think about this process and what is the nature of this process. So I'm just telling you, for example, we get a negative number, and now we ask you to analyze this system and predict how does your entropy change in this case. Now, we have a negative delta G that equals to delta H minus T delta S. So for a pure substances, we're only changing the pressure, we're keeping the temperature the same, so your delta H will be 0. And since we have a negative delta G, what it means, well, your delta S must be a positive process. All right, so the take-home message you can get, like some of the chemical insight you can get, is because we did our calculation, we find out delta G is a negative number for this process. You can predict the entropy to be increasing when we are reducing the pressure of that species. And if you think about it, it actually makes sense, right? When you're reducing the pressure, the volume increase and the entropy naturally increase with it. Just to make a little bit connection to what we discussed before. Okay, so this one basically is we introduced 2 terms. The first one, partial pressure, and then the chemical potential using partial pressure. And let's move on to our next part. So we have 6.2. Now we're ready to talk about chemical equilibrium or reaction equilibrium involving ideal gases. So when we are talking about equilibrium, a few things we know. For example, we know that zero at equilibrium reaction. So this symbol means we have an equilibrium reaction that is described to be the stoichiometric coefficient times species AI. All right, so that's a reaction that's at equilibrium. Now, what do we know about a reaction that is at equilibrium? We know the total chemical potential must equal to 0. All right, so on the left-hand side, that's a reaction. On the right-hand side, that's the chemical potential. And then we're ready to define an equilibrium constant for that process. Now, let's look at it. We're talking about the standard equilibrium constant. Let's start from a example equation. We will generalize our derivation later on. So let's start with a simple reaction, like A times big A plus B times big B react to give C big C and D big C, D. So small a, B, and C, D here are your stoichiometric coefficient. Big A, B, C, D here representing the chemical species we're interested in. So what do we know about this process? What we know is at equilibrium, the total chemical potential equals to 0. So if we write out our coefficient and the chemical species, what do we have? It's a small c, mu c, plus small d, mu d, minus small a, mu a, minus small b, mu b, equals to 0. Right. So that's just writing out this expression using that specific equation of interest. And we have an expression for the chemical potential of each of these species involved in the reaction. So this part, then we just write it out using this equation here. Because your chemical potential of that species I equals to the standard chemical potential plus RT ln P of that species I over P naught. So write it out, it's going to be a really long equation, but the nature is pretty much the same, right? So you have C times mu naught of C plus RT ln PC over P naught plus D times mu naught of D plus RT ln PD over P naught minus A times mu naught A plus RT ln PA over P naught minus B mu naught B plus RT ln PB over P naught. And this whole thing goes to 0. Nothing special, we're just writing out the expression for the chemical potential. And we want to simplify it a little bit. Right now it looks too complicated and we cannot get any information out of it. So let's move all chemical potential to the left. Right, so we want to express our chemical potential with some property we can measure, like pressure. So in this case, we're moving all the chemical potential to the left-hand side, and we end up getting C mu naught C plus D mu naught D minus A mu naught A minus B mu naught B. And everything left on the right-hand side are your RT ln term. So what do we have? Let's say negative RT, you're just taking that constant out. You have your coefficient C ln PC over P naught plus D ln PD over P naught minus A ln PA over P naught minus B ln PB over P naught. All right, just moving the terms. And on the left-hand side, let's just focusing on the left-hand side for now. If we only care about the left-hand side, now this whole thing effectively equals to your molar Gibbs free energy of that specific substance. So that is your C times your molar Gibbs free energy of compound C plus D G naught MC minus A minus B times your molar Gibbs free energy. It's a very ugly B. Or what we can do is write that out. Obviously, that equals to the summation of all your coefficients, G naught M of species I, and we went over that. One second. Okay, come back. Okay, we went over that, and it just equals to your overall delta G naught of the reaction, right? So that's the standard Gibbs free energy change of the reaction. So that's what we have on the left-hand side. And what about the right-hand side? So this is on the left-hand side. This whole thing becomes delta G naught. And on the right-hand side, we can do the same thing to simplify all those logarithm terms. So this whole thing comes down. Well, and you can simplify it by writing it as RT and everything in the logarithm. So you have the, on the top, that's the PC over P naught with coefficient C, PD over P naught with coefficient D. And on the bottom for the reactant, you have PA over P naught with coefficient A, and PB over P naught with coefficient B. And this thing equals to your delta G naught. So basically what we did here is using the definition of your chemical potential, and we find out this relationship between your Gibbs free energy of the reaction and something experimentally you can measure. And this whole thing here, that leads us to our definition for our standard equilibrium constant. You sort of see it coming, right? So then we use this whole thing to define our standard equilibrium constant. So my Kp for the reaction AA plus BB goes to CC and DD, thus equals to this term here. And we have delta G naught equals to negative RT ln Kp. All right. So this whole derivation, you can imagine now instead of having only two reactant and two products, we can further extend it to our generalized reaction, where you have 0 goes to all the summation of coefficient times species. So before we move on, any questions? Yes.
Going back to like before step 3.
Here?
Yeah, for the negative RT and the rest of the term, why is the coefficients there again?
So this coefficient is outside the bracket, so it will move in there.
But then on the left-hand side, you also have
Right, so if we write out this term here, right, we have C mu C naught plus C RT.
Oh, I'm sorry.
Yeah, right, it has to stay there, so. Any other questions? Okay, sounds good. And then we're ready to extend whatever we just derived to give a more general definition for our equilibrium constant. So the way we do it is let's extend that derivation to a general ideal gas reaction. So for this general reaction here, that's a summation of all the coefficients and your species. So at equilibrium, what we have is delta G naught equals to negative RT ln K naught P. So that naught means it's standard state. And the definition of Kp here, that again, we have this new mathematical operator. So this term looks horrifying. It just means it's a product of everything. So for example, if we use a easier one of like just AI, this operator just tells you it's a product of like A1 times A2 times A3 goes all the way to AN. Now your equilibrium constant is defined as a product of your partial pressure at equilibrium over your standard pressure, P naught, with the coefficient on the power. All right, so remember what we have? It's the same thing. So these are the ratio between your partial pressure over the standard pressure. You have the coefficient on that power. Now, if it is a reactant, it's on the bottom, or this one is actually negative A. And one more step we can do is the same as like delta G equals to negative RT ln Kp. You can also write K naught P equals exponential of negative delta G naught over RT. All right. So again, what we have is for ideal gases, we have a way to write out our delta G. So your delta G naught equals to the summation of all these G naught MTI of the molar standard Gibbs free energy. And for each of these species, the pure molar Gibbs free energy equals to its chemical potential, mu I, summation of the mu I. So some of the things we can find from tabulated data, right? If we're looking at 298 Kelvin reaction, or for some other Kelvin, you can also find tabulated data for your molar Gibbs free energy. So with that in hand, you can calculate your Kp equals to exponential of negative G naught over RT. And with that Kp linked to the component of your ideal gas species, now what we know is we can predict what is the component of your ideal gas mixture at the equilibrium of any ideal gas reactions. All right. So I don't think I have enough time to finish that example with you. So for midterm 2, anything on equilibrium constant will just be conceptual question. It's not going to be a calculation. But in the next Wednesday class, before Thanksgiving, we'll do an example together and also talk about the dependence of temperature of your equilibrium constant, Kp. I'm like 5 minutes ahead of time, so I want to give you a few like quick comments on how to prepare for midterm 2. I got that question like through email a lot. So one of the things I got to ask is we have so many equations. How can I study for those equations? How can I set up a calculation? So my best answer to that is you read the question like several times and make sure you understand what that question is asking for. don't just grab a equation and start doing calculation. You're almost bound to get it wrong. So that's one thing. Second thing is, although our exam is open book, open note, you shouldn't be studying for a concept during the exam. So in the exam, if the question is asking for a concept, you have no idea what it's talking about, I highly recommend you just skip that question and come back later. Because if you're like trying to study for that concept during the exam, you probably don't have enough time to solve that problem. Okay, and that's two general pieces of information. And let's just quickly go over the lecture note and just raise your hand. I'll pause and ask you to raise your hand if you want me to do an example question on our Friday lecture, and we'll see how that goes. So last time we finished at the end of lecture 7, which is mixing of different inert perfect gases at constant PT. So do you want me to do more example on this one? So, okay, raise your hand if you want me to do more practice example on this topic. Okay. And let me just write it down. Okay, next up, lecture 8. So this one talks about the relationship between entropy and reversibility, irreversibility. We also went over the physical meaning of entropy and give a more easy way to define the second law of thermodynamics. So raise your hand if you want us to do more example here. So this one, you have the adiabatic processes and talking about that relationship to the second law of thermodynamics. Okay, yeah, so raise your hand if you want to see more example. You know, if you raise your hand to every question, I'm just gonna randomly pick from them. Okay, lecture 8. Lecture 9 is the one, I think it's more like conceptually challenging. So this one, we went over the idea of equilibrium. We started talking about the relationship between your like material equilibrium with entropy. We get to the point in understanding that entropy is maximized at equilibrium. And then we start introducing the concept of Holmes free energy A and also Gibbs free energy G, like their definition, how to use them, like what exactly they mean, and what their physical meanings are. So raise your hand if you want me to spend more time on Gibbs free energy or Holmes free energy. Okay. And then at the end, we have our thermodynamic relationships in this chapter. So that's we start from the 6 fundamental equations. We went over the derivation in, say, like how they are actually linked using the Gibbs equation, and how to solve for the Gibbs equation, how to derive the Gibbs equation, how to use the Gibbs equation to find out relationship between your specific thermodynamic property and these partial derivatives. We also went over the Euler's reciprocity relations to build a link between your different partial derivatives. And at the end of this lecture, we went over the Maxwell relations and also how to use the Maxwell relations to solve for like volume dependence or pressure dependence of your external state functions. So raise your hand if you want me to spend more time doing an example on this one. Okay, that's a little bit surprising, but it's okay. Next one. If you change your mind, you can still let me know, you know. Did you change your mind? You want us to go over the Gibbs relations? Okay.
I feel like on our homework we haven't had questions that have like really gotten into that. So I guess I don't really know what to expect.
Okay, sounds good.
On the exam, would you want us to derive those relationships, or
maybe.
can we just?
Right, it depends on the question.
If it's not asking for it, but you have to use it. Do you
Oh
want
no,
to
you don't have to derive it
but it's
if the question is not asking for it. And then lecture 12, we went over calculation in change of these state functions. So we have like how to calculate delta S, how to calculate delta H, and etc. So these are our setup calculation. I'm just bringing your memory to that. And when we're calculating entropy, you need to build a reversible path that you like for that calculation to take place. Also for delta H and delta U, that's the same idea. Do you want to see more example on these? Raise your hand if you want to see more example on this one. Okay, so this one is 12. And we have our equilibrium. We went over the concept of chemical potential and material equilibrium. We introduced the idea of chemical potential, and we went over a sort of derivation in what exactly is chemical potential. We end up at talking about the nature or the physical meaning of chemical potential by building a link between chemical potential and temperature, and we also went over that today. So this part is pretty conceptual. So if you have any, we want me to do more example on this one? No? Okay. And the setup of reaction equilibrium, like what are stoichiometric numbers and what exactly we're talking about. So how to use that stoichiometric number and also the extent of reaction to calculate for properties of a chemical reaction. So raise your hand if you want me to do more example on this one. Okay, sort of. So lecture 12 in general. Okay. I'm almost there, I promise. Okay, 13, so these are just using the table of thermodynamics and know where that table comes from. So anyone want us to do more example on this one? And also the Hess law and how to calculate heat of reaction and etc. Okay, no. 14, so this one is how do we define conventional entropy, the third law of thermodynamics, and how do we get to the conventional entropy in the thermodynamic table. So remember that 9-step, a little bit tedious processes here. And then how to calculate the entropy of the reaction and Gibbs free energy of the reaction. So raise your hand if you want me to do more. Okay, this one is overwhelmingly yes. Okay, and that's 14. And 15, yeah, this one we haven't get into it. It's just a conceptual question. Okay, I know what to do. I'll send out a information later today regarding like detailed things you need to know for midterm 2.